And I would also like to thank the organizers for the opportunity to present the results here. So what I'm going to address is the question one, where we are supposed to know if we could extract some useful or optimal information from the path. And what I'm going to tell you today is if one could do the good projective measurements of a qubit that is coupled to the environment, then the measurement statistics itself could induce certain properties of the path. And that way, we get to know the path as well as a possibility to manipulate it so that one could achieve the target quantum state engineering of it. So the experiments, I'll show you a bit of theory and experimental results. Experiments are mostly done by Sen Yang, who is currently at the Chinese University of Hong Kong. And we are a part of the big group of York Rock at Stuttgart. So just like a brief overview, I think morning already Alex gave a good tutorial for NV-based quantum sensing. So I'll skip the introduction of the physical system and I'll briefly reduce the slides for the introduction. And then I'll tell you what's happening to the path when a qubit coupled to it is repetitively measured. Then I'm going to tell you some theory examples which we tested first to know if this is really the case. And then we started doing some experiments and we got some interesting results which I'm going to share with you. And finally, I'll tell you how the problem can be mapped into like a machine learning problem where one could use reinforcement like algorithms to predict what are the best measurement scenario to achieve a certain quantum many body entangled state, for example. So the problem in hand is the central spin model, and we consider a simple dephasing kind of a model where, as you see, the central spin is represented by S and the environment spins by I. Okay, and then we have here a pictorial depiction where there is a central spin, which in our case is the NV center spin diamond, the electron spin, which we call it here as an ancillary qubit, whereas the nuclear spins that are distributed around are the computational qubits. As you can see, there are nuclear spins which could be coherently controlled, and there are certain nuclear spins which are far away and are not possible to be coherently coupled. So here I don't make any distinction of such coherently and incoherently coupled paths. I just consider the overall path where a certain spins are interacting strongly and certain weakly. Now, if you look at the general scenario, we always have paths which are unpolarized, the thermal states. Okay, and normally we tend to save the coherence of the central spin, so we employ different unitary controls, which partly you're also hearing in the morning's talk, where we do like a CPMG or band control to protect the coherence of the central spin. Um, but there is other ways of also controlling the coherence of the central spin, where if we possibly modify the path itself in a way that the path is pushed into a state that is least coupled to the central spin. If one could do that, then we also achieve the same decoherence control. So modifying the bath or like controlling the bath has been achieved by different ways. For example, like the old NMR trick where you try to polarize the spins itself so as to reduce the statistical noise and thereby improving the coherence of the central spin. Or one could use these adaptive protocols. For example, if you look at recent papers from Christian, he'll tell you like how one could adjust, for example, a certain control on the central spin through a feedback kind of protocols. And there's also other way which was considered earlier by Michel Lucan and his group. It's like if one could possibly freeze a nuclear spin configuration, that too that would have also influence on the dynamics of the central spin. But here, what we are interested is, as I said, that all of these different methods are targeted for a improved performance of the central spin. But what we are interested here is, if all of these are in certain sense trying to learn a certain aspect of the path and then trying to adjust your central spin in accordance so as to have an improved performance of the central spin, then what could be the role of repetitive measurements and looking at the statistics of such a qubit coupled to a path. So this is the scenario that I'm interested to explore theoretically and experimentally. Here I have a central spin system and a path. And what I'm doing is I'm just letting it create a superposition of the central spin, then let it evolve through this interaction with the path, and then measure it back in the energy basis. And now I do this repetitively, which means that now the state of the bath after the first measurement is not the same as its initial state. So in that sense, the bath accumulates the kind of a memory, or the bath itself is changing due to every measurement caused on the central spin coupled to it. Uh, Maybe this is not new. This is something that people have been doing from long time. This is the noble work of Harash and Boylan. So, for example, here all they're doing is they're sending in atoms, single atoms in the Rydberg state, and so they have a finite time in which they are coupled to a microwave cavity, and they're being read out. Right? So it's exactly like this. So you have a superposition, this initial, and then it evolves interaction with the cavity. Again, you do another Hadamard and then measure. And what one is typically observing in such experiments is some kind of jump statistics. So these are the famous quantum jumps. And what one also have used is that if one could figure out what is happening to the cavity field for a certain string of measurements, then what one sees is like one could create fox states, one could create cat states, and a lot. So this review will tell you that all the game can play by actually selecting a certain measurement string here. So for our system, since we don't have such flying atoms to the cavity, all we could do is we could create a superposition, let it evolve with the path, measure, and then reinitialize it, and then start the process again. So it's the same NV center, like here, these atoms, which is being reused again and again. And because we are interested in exact projective measurements of the electron spin, so we use the well-resolved optical transitions at low temperature to achieve the single shot readout. So just like here, one could also observe jump statistics. Well, and now we want to ask, like starting from a thermal state of the bath, and exactly similar to a cavity here, what we have here is a spin bath during this evolution time. And the spin bath to start with is in a thermal state, and now we want to ask, is there a certain measurement string that allows this to collapse into either, like for example, a GZ state, or something like a resonance valence bond state where all of these are like singlet paired, and so on and so forth. So first, just like to quickly, maybe I will not spend time here. I'll quickly skip this, but you could see that you're measuring on a strong measurement, and the effect of that is that the system subsystem B is evolving in a non-unitary fashion, because you don't have a unitary, you have a unitary evolution in the total, but then on B you have a non-unitary evolution. Because of that, what could happen is you can increase the entropy is no more conserved. For that reason, the system B could be polarized or unpolarized, and so on. So a strong measurement on A implies a weak measurement on B. And now the controllable parameters that you have in the experiment on the calculation is this time tau, the time you evolve, and if there is any control fields that you want to apply on system B, A, and the choice, measurement basis choice in which you want to measure the system A. Given all this, so what we tested is that, for example, if you take a NV center coupled to a spin path, then it's possible that for a certain choice of measurement, where we, let us say, we post select that the measurement always shows, let us say, a spin up of this central spin. Then, interestingly, what one could choose is from a certain choice of tau on the applied field, you can break the whole spin ensemble into singlet pairs, right? And then and that is one of the like steady states of the dynamics, through which the central spin doesn't decohere anymore. Or we have used, for example, the same measurements to cool cantilevers. So in this case, what you see is that a thermal state, starting from a thermal state, right, here, the role of measurements is to change this distribution function through a measurement induced filter function. That's a normally we are used a filter function in dynamical decontrol, right, which is induced by unitary pulses. But here you also can create a filter function which will try to um, like remove unwanted thermal excitations and only keep certain, so that an initial thermal state can be either collapsed to a ground state, cool state, or to a squeeze state. Then we went on to experiments, and then this is the scenario we had. So we wanted, so our qubit basis is this +1 and -1, okay, and then the single shot readout is performed by this transition 0 to EX, and the polarization to this state, initial state initialization, is done through the other laser A1. So what we have is a microwave pipers which is creating the superposition. Then we let it evolve for a certain time tau. Again, do this by half pulse, which is like returning back to this, and then you read out. So if you do this in a normal FID experiment, what you see is this, like the Ramsey. So you see the decay, where the decay gives you the T2 star time, which, for example, in this case is um, like for example, this time where the initial coherence is completely decays is like around 1.2 microsecond. And this is just to tell you exactly what is happening in this pulse sequence. So you polarize it, then you apply this microwave to go this, then there's evolution where it picks up a pace, and then the next micropulse will do this. Right? So all of this is something that is happening to the central spin, but equally there is also something happening to the bath, and that's what we want to explore. So if one now starts to make a series of, so the experiment goes in this way, that we want to now repeatedly measure the central spin at this time scale tau. Now, because as you see, it's completely decohered, so it's just equally probable to be found on both sides of the equator with the equal probability. So this is just like a classical coin, right? And also because our interaction is simple dephasing interaction, so there is no direct polarization exchange with the bath, right? So this is two simplest of the model that we have. Even with this such Hamiltonian, repeated measurements will create something non-trivial. So what we do is we do 4 measurements. Okay. So we initialize, evolve, measure, again initialize, evolve, measure. And so because we do 4 measurements, there are 16 possible measurement strings, right? 0, 0, 0, all the way to 1, 1, 1. Now, if it's like a classical coin, then you would expect all of these measurement strings to be equally probable, because both 0 and 1 are equally probable. That's the flat line that one should expect. But now if you take into consideration that the measurement back action on the path, then what you see is like each measurement changes the path, which in turn changes the result of the next measurement, and then you start seeing a different statistical measurement statistics. And now, in fact, if you do the experiment, this is exactly what you find. So here, for example, we did something like 60,000 repetitions of the experiment, which consists of 4 consecutive measurements, and then we picked up the statistics, and they exactly look like what we should expect from our simulation. So why is this happening? like if you want to tell me. For this, maybe the four measurement may not be good to come to conclusion. So what we did is we just did a lot of measurements, like 250 measurements, and then um, for each of these we call as these trajectories is like the repetition of an experiment having 250 measurements, right? So and the blue and the yellow dots correspond to uh, the measurement being 0 or 1. And what we see is like if you now plot the a string length, for example, 0, 0, 0, 0, 0, 0, 0, 0. So the number of zeros in the measurement that corresponds here to the string length. So if you plot that and you ask what is the coincidence at which they occur, so normally if you have like a classical case, then what one should expect is a Gaussian, because all of these are equally probable, and the maximum is that where half of them are zeros and half of them are ones. But experimentally what you see is like a completely different statistics which mimics something like a quantum random walk. So now if you ask like, is there really a random walk happening? Then what you see is like, indeed, yes, because each measurement has two possible evolutions for the bar and so on. Each measurement further has two possible evolutions for the bar. And all of these are connected through the central spin superposition. So that's what is a normal random walk. So what is happening is like if you take a normal quantum random walk, but now you induce some kind of a probing, that is you probe it in the sense like you ask you do a random walk and then you project the coin onto the plus state or the minus state, and now you ask what is the probability that at the end of the walk that you see the different possible projection results. So because it's like again like four measurements, then you have all zeros, all ones, and that exactly shows something like a quantum random walk itself. If you do the same for classical random walk, which we have a Gaussian, then as expected, all of these would be equally probable and you get like a flat distribution, in the sense that the measurement statistics try to transduce the physical behavior of the system. In that sense, our measurement statistics of the central spin is transducing certain behavior of the environment itself. And what useful effects can this have? So this is interesting. And what you see is there is a drastic improvement of the T2 star. For example, just for four measurements, already you see there's a quite a difference in the T2 star. This is because, so what we do is we do a set of four measurements and then perform FID. Okay, so you measure the coherence of the central spin after the measurements. So these four measurements are modifying the path, and on that modified path, if you ask how is the coherence of my central spin surviving, it is better. And in fact, if one looks, this is more for the experts on, with spin systems, what one sees is that the ODMR line itself gets squeezed. So in fact, the measurements are actually modifying the path in a useful manner. And what we also see is that here, for example, this is the probability that if n measurements are identical, what is the probability that the n plus 1th measurement is also the same? So that you see is actually saturating, which means that it is more and more probable to have identical measurements, which would imply that the bath itself is stabilizing to a certain state. And what one can ask even more is that can one observe xeno and anti-xeno effects? Is, for example, like if you measured the four measurements resulted in all zeros, and now you ask what is happening to the post dynamics of the qubit, then you see that the red line is the normal FID. So you can have a slower decay, which is like xeno, and if the previous four measurements were in the result 111, then you have a faster decay like the anti-xeno. And the experiments also showed something similar. So we need to average here more to get better statistics. But in that case, what we see is like the path that you prepared by measurement is also helping you to affect the future evolution. I'll quickly tell this other example. So we also see this, for example, in correlation measurements. We ask like we do four measurements, wait for a time, and then do four measurements. So if the path state is unchanged, then the result of the next measurement should also be the same. That's what we see here. That indeed that um, that the similar measurements are unchanged up to a time separation of 1 second and to max of 2.5 seconds. So which is clearly an indication that uh, a stabilized bath, that a bath is being stabilized by these few measurements. And further, like we also see an extreme enhancement of the coherence of the central spin when we do such measurements, where you start with a superposition state, wait for something like almost like less than a millisecond time, and even then you see that its coherence is maintained because the same measurement outcome is seen. So now the goal is finally to see, because here we explored only one possible measurement string and how it affects, gives rise to some useful effects for the central spin. So in general, we would like to explore like, can one use this map to a learning problem where the agent can learn through the dynamics that yeah, so yes, I'm almost done. So in this, there's a general scenario for the learn protocol. So there's an agent who performs actions depending upon um, uh, the the environment state. Like say, so there's a state space, and there is an action sequence. And if he has done the right action sequence to take uh, it through the right state, then you get a reward. So this is a normal scenario. And in our case, um, because we are dealing with quantum states, right? So the state space here for us is large and continuous. So what one needs to do is like one has to go through this deep Q network where an artificial neural network is used, for example, to get an optimal Q value function, which would then optimize the Bellman equation to get something. So, for example, like for two qubits, two spin nuclear spin bath, if you want to prepare a singlet state, then what we see is like the learning helps the agent to find the right actions where he could maximize the fidelity uh, to form the singlet state, and when compared to a randomly chosen measurements. For example, you want to measure in the z basis, x basis, or y basis, so that is given as free parameter for the agent to choose as action sequences. And what he sees is like when this learning when compared to random choice of these measurements, one sees that one could always prepare this singlet state. And further, the agent here could also learn, because our calculations only indicated, for example, a preparation of singlet for a measurement which corresponds to the first. That is, you do two x basis measurements. But for example, the agent could also find out many other measurement strings and so on, to which could lead to the same state preparation. So the end goal, like for example, with machine learning, is that one would like to have a target state to prepare in mind, and now you can ask for what is the kind of measurement sequence that I need, for example, to prepare such a state. Either that could be a target state, or it could be the implementation of a computation itself. Just to summarize, so what I told you is that measurement statistics could help reflect directly the path dynamics. The path itself could be used as a memory for past measurements, and as I was showing, like this could also be used for some quantum information protocols like error correction. And there are also this measurement, because we are anyhow doing a measurement or like a dissipative protocol. So one can think of performing quantum computing itself, and the result of quantum computation could then be used as a parameter to give the reward to the agent who's trying to find appropriate action for the circuit. So with that, I would like to thank the group. So this group is led by Professor Bakro, and we are all together. So I thank you all for your attention, and I would be happy to take some questions.
Thanks, Durga, very much. Any questions out there? There's probably time for one or so. Let me maybe ask one. So you see this quite cool thing that the bath isn't changed for a second or even more. So what is the relevant time scale there? It's like T2, I guess, no?
Yeah, so the electron, because here it's like it is the correlation between the measurements. So given 4 measurements which are the same, you ask how much you wait again to see the same 4 measurements with the same result.
Yeah.
So in that sense, it's not directly T2. It's because you initialize the electron spin before the measurement.
Yeah. Okay. Yeah.
Okay. But the other measurement was showing something like close to the 4K T2 of electron spin, which was around like 1.4 seconds.
Yeah.
So it came to that value, something like 0.9 second or something.
Yeah. Makes sense. Yeah. Thanks a lot.
Yeah. Thank you. Yeah.
So time to move on to the next speaker, which is Luca Pezze from the National Institute of Optics in Florence.
Okay. Can you hear me?
Yeah, we can hear you and see you. So good.
Okay, very good. You can also see me. Good. Okay. Okay, so hello to everybody. I'm Luca Pezze. I'm a researcher from the National Institute of Optics in Florence and the European Laboratory of Nonlinear Spectroscopy. And today I will tell you about parameter estimation based on classification and regression with machine learning. And this work has been done in collaboration with Samuel Nolan, which is a postdoc in our group, and Augusto Smerzi. And of course, I would like to thank a lot the organizers for the invitation to give a talk at this nice conference. So in a nutshell, quantum parameter estimation, which is the main topic of my talk, is based on 4 key steps. So first we have a state preparation. And in general, I will consider the preparation of some state of n qubits, possibly in some highly entangled state. After this state preparation, we have parameter encoding. So a transformation, a generic quantum channel that depends on the parameter theta. Theta is here unknown and is the quantity we want to estimate. In the simplest case, this quantum channel is a unitary transformation, but we don't want to do any assumption on the transformation. Then we make measurement on the output state. So we choose a measurement operator and we indicate with mu the possible result of a measurement. And okay, and after the measurement, so once we collect the measurement result, we have an estimator. And the estimator is a function of the results that returns an estimate of theta. And the goal is to minimize the uncertainty of this estimate. So we want that theta est, given the measurement result, is as close as possible to theta. And in this talk, I will mainly focus on the optimization of this part using machine learning techniques. Actually, in the ideal case, where we have a perfect knowledge of the conditional probability distribution of the output state, so the probability to obtain a measurement result mu given parameter theta, if this is known for every mu and every theta, then we know already from literature what are the efficient and optimal strategy for parameter estimation. And these are at least asymptotically in the number of repeated measurements. These are the maximum likelihood and Bayesian that are equally efficient, so they reach the same uncertainty, even though they are conceptually very different. And I will return later on this. The problem is that, of course, experimentally, these probabilities are not known. So we don't know this probability, even in, I would say, simple experiments, perfectly for every theta and every mu. So there are alternative practical approaches to this ideal theoretical and optimal approaches I discussed. So one possibility is to consider simple fitting model of this probability distribution. And this works fine for simple system of one or few qubits. And this has been applied successfully in the literature. However, if we have system of many qubits and possibly in a very highly entangled state, finding a simple fitting model of the probability is very cumbersome. In general, these probabilities are very complicated and have many peaks and strange features. And a bad fitting would introduce biases and an overestimation or an underestimation of the uncertainty, which is bad. An alternative approach, which is used in system of many qubits, such as atomic clock or atom interferometers, is the so-called method of moments. So it's an estimation that is based on the knowledge of low-order moments of the probability. However, this method neglects important information that can be contained in high-order moments of the probability distribution. This is not captured by these simple methods. So in this talk, I want to use an alternative and new approach, that is to use machine learning. And the idea is that machine learning can be used to capture the key feature of the probability distribution. So the idea is that maybe we don't need to know everything, every detail of the probability distribution. Maybe we just need to capture the key feature of this probability distribution. And hopefully the machine learning is able to capture these features. And I will exploit this idea for parameter estimation. And first I will discuss Bayesian estimation based on probabilistic classification. And then I will tell you about frequentist estimation, in particular maximum likelihood based on regression. So let me start with the Bayesian estimation. And let me go back to the ideal case. So the case where we know exactly what is this conditional probability distribution as a function of mu and theta. So the idea here is that theta, the unknown parameter, is fixed while we do the experiment, and we collect measurement data according to this probability that characterize the apparatus. And then we apply the Bayes theorem to do an inversion. So the Bayes theorem returns a probability distribution for a variable phi given mu. And the meaning of this probability distribution, this Bayesian posterior, is a degree of belief that the variable phi that is used here in the theorem is equal to theta, the true value of the parameter that has generated the data, given the measurement results. So here I'm showing just a cartoon of this Bayesian probability distribution. And once we have this function, which is normalized to 1, we can choose, for instance, the mean value as Bayesian estimator, and the uncertainty is given by a confidence interval around this estimate. For instance, the variance are shown as shown in this equation. And the key feature of the Bayes theorem is that there is it contains this additional quantity PD phi, and PD phi is the prior or our subjective knowledge about theta before doing any measurement. if you don't know anything about theta, can be even just a flat function. But in general, we always need a subjective, I would say, entries in the Bayesian theorem. The next feature of the Bayes estimation is that for many measurements, so asymptotically in the number of repeated measurements, the Bayesian distribution, any Bayesian distribution for any model and any prior, converges to a Gaussian centered around the true value of the parameter theta, and with the width given by 1 over the square root of m, which is the number of repeated measurement, times f, which is the Fisher information. So this is the ideal case. And now I turn to how we do this, realize this with a neural network. So first of all, we need the training of the network. And to do this, we divide the possible values of theta in a grid of d points. Okay, so consider a grid, and this grid will be my output layer. For instance, this can go from 0 to 2 pi, for instance, if it's a phase shift. Then we set, for every value of theta j, we acquire nj random data for theta j. We calculate the relative frequency of the possible results mu, okay, which is this possible result mu here go from 1 to k, and this relative frequency represents my input layer, okay, and for given theta j, I force this frequency result, this frequency distribution to corresponds in output to exactly the corresponding theta j. So the output will be 0, 0, 0, 1, and 0 as well. This is what I forced for the learning, for the training. Then we do parameter estimation using the trained network. So we set theta to an unknown value, but fixed, and we collect experimental results. So for a single experimental result, the input will be 0 for every value of mu, except for the corresponding mu here, that will be 1. So this is this kind of delta function. And in general, we obtain an output, which is a distribution like this. And we call it P of theta j given mu. So what are the properties of the output of the neural network? So our result or our claim is that the output of the neural network is a posterior Bayesian distribution. Okay. So in a sense, the network performs intrinsically the Bayesian inversion, and given some knowledge about the likelihood, returns a Bayesian posterior. To convince that this is actually correct, we do two things in the following. First, we give a meaning to the prior, and then we show that the Bayesian update converts to the Gaussian distribution with the right width. Okay, so what is the subjective prior here? So we set up here an equation that's given the measurement, the training data is able to calculate the Bayesian prior. So in the first passage, we do nothing. We just use that probability sum up to 1, and then we use the Bayes rule. And in the last equation, we replace this PD mu with the normalization of the Bayesian distribution. Now we have an equation where P, the prior, appears on both sides. And we can solve numerically this equation as an eigenvalue equation. And here are the results. So here I'm showing on the left the number of training data for each theta j as a function of theta j. So this is the number of data with which we train the network. And on the right side, I show the corresponding prior that is calculated with the equation I show you. So you see that there is a one-to-one correspondence between the training and the prior. So we identify the Bayesian prior as the distribution of training data. So I told you the Bayesian prior is something subjective, and also indeed the way we train the network is a subjective choice. So subjectivity is recovered in a sense. Then we want to investigate the asymptotic properties of the Bayesian distribution. So I told you we need to multiply distribution corresponding to different measurement results. And what we want to show is that this goes to the uncertainty of this distribution goes to the inverse Fisher information. So these are the results for a single qubit. So we take a qubit spin up, we apply rotation around the x-axis, and then we project on spin up, we measure on spin up and spin down. And this is the output state, actually. So these are the result of the training of the network. So this line is obtained if we obtain a measurement result that is a spin up result or a spin down result. Okay, so this is the training, and for the estimation we collect measurement result spin up and spin down, so a certain number of spin up and a certain number of spin down, and multiply this distribution. And here I show the result for 10 measurements and for 100 measurements, and you see that the distribution is essentially Gaussian. That's shrinks as we increase the number of measurements and centers around the true value of the parameter. And here I show the result of the Bayesian width as a function of number of training data. Here the number of measurements is equal to 50, and we see that the Bayesian width converges as we want to the Kramer-Rao bound. So 1 over square root of the number of measurements times the Fisher information. So this is obtained for a large number of measurements, good training, and dense grid. And I will come later on this optimal choice of parameters for the network. This was for a single qubit. We have repeated the analysis also for more complex state of many qubits. For instance, here we show the result for 10 qubits in a twin Fock state. So a symmetric quantum superposition of n-half particles spin up and n-half particles spin down. So this is a highly entangled state. Each qubit is rotated by an angle theta around a certain axis. And here we show the result. And again, we see that a convergence toward the Kramer-Rao bound if the network is well trained. And of course, we have also repeated the analysis for including noise. This is an example of depolarized twin Fock state. And you see again that it converges to the Kramer-Rao bound as we expect. Okay, of course, the noise here is included in the training, and we assume that the noise in the training is the same as the noise when we do the actual parameter estimation. So far I discussed about Bayesian estimation based on probabilistic classification. I told you about the interpretation, the subjective interpretation of the prior knowledge identified by the training process. And I told you how the Bayesian width converges to the Kramer-Rao. Next, I will tell you about frequentist and in particular maximum likelihood estimation based on regression. So let me step back once again and tell you about the maximum likelihood estimation in the ideal case. So when these conditional probability distribution are perfectly known. So the maximum likelihood consists of the following. So we do measurement for a certain value of theta. We collect the results. And then the maximum likelihood estimator is the value that maximizes this likelihood function. So the probability of mu as a function of phi here. So the maximum likelihood is a number given some measurement result. And of course, since the measurement results are stochastic, also this maximum likelihood estimate is stochastic. So it has a certain distribution, and from this distribution that is obtained by repeating many times the estimation, we obtain a width. And this width is the uncertainty, frequent is the uncertainty of the quantify the statistical fluctuations of the estimator. And once again, we have very nice asymptotic properties. So for a large number of measurement, repeated measurement, the distribution of the maximum likelihood, so this kind of histogram, converges to a Gaussian with a width given by 1 over number of measurement times the Fisher information, which is the Kramer-Rao lower bound. So this is exactly the same result as the Bayesian case, but obtained for a very different, in a very different way. So to realize this frequentist estimation with machine learning, first we do a training, and the training is exactly the same as we have done before. So we divide the possible values of theta in a grid of the point, and for every theta j, we acquire measurement results. But now the output is not a grid, but is a single output. And this gives a function of the input training data. And we optimize this function by minimizing a cost function, as usual. This is the basic of regression. So at the end of the training, we obtain a function of the measurement data. So for parameter estimation, we set theta to a certain value. We acquire m measurement results, mu1, mu_m, and then we apply this function. And this gives an estimate of theta. So let me discuss the properties of these estimates. So let me point out that there are three important quantities, numbers here. One is the number of measurements doing for the estimation, m. One is the average number of training data used for the training for each value of theta j, and one is the number of points in the grid, d. So if we obtain numerically that our estimate for a small number of measurement m is given them by the maximum a posteriori Bayesian estimate. So the maximum a posteriori Bayesian estimate is the maximum of this function. So this is very similar to the maximum likelihood, but it also contains the prior. And the prior is again identified by the number of training data for each theta j value. For a sufficiently large number of measurements, the prior here becomes irrelevant, and the estimator that we obtain by training the neural network is exactly the maximum likelihood estimate. So the sensitivity of this estimator converges to the Kramer-Rao bound. The number of measurements to have this crossover is roughly obtained by this condition, which can be obtained for the Van Dries bound, actually, where m times the Fisher information is approximately equal to this quantity, which can be interpreted as a Fisher information of the prior. So here I show a result of simulation, where I plot the behavior of the maximum likelihood estimate in the ideal case, okay, the orange line, and our estimate theta w for a very peaked prior in such a way to have to enhance the role of the prior. And you see that there is a disagreement with the maximum likelihood. And finally, for a large number of measurements, the two agree. And this dashed line corresponds exactly to this condition here. So asymptotically in the number of measurements, our machine learning estimate has a sensitivity that converges to the Kramer-Rao bound. Let me now tell you about the parameter for the machine learning training. So the most obvious regime is condition is that we need a good training. So if we want to do an estimation with M measurement, we need to train the network with the number of training data much larger than M. This is a rather obvious condition. And much less obvious is what happens as a function of the grid size. That plays a very important role. So if we now look at this plane, so we want to find a good training condition as a function of the grid size, number of grid points, and number of training data for each theta value. And the condition that we find is that we have a good training where the different theta j value in the grid, in the training grid, are statistically distinguishable. So the distance between these theta value, that is of the order of 1 over d, is much larger or larger than the statistical distinguishability of the training data, which is quantified by 1 over n bar, the average number of training data, times the efficient information. So this identifies a curve here, which quantify the points that fulfill, parameters that fulfill this condition are a good training regime. So here I show, for instance, what happens as a function of the number of grid points. Here I plot the difference between the maximum likelihood estimate and our estimate, machine learning estimate, as a function of d for different values of n bar. So this would correspond schematically by these blue and green arrows. So you see that the two estimates, maximum likelihood and the machine learning, tends to agree until a certain point where the agreement stops. Okay, and this is exactly obtained when crossing these lines. This line, okay. And you see that if you increase the number of training data, this asymptotic convergence is reached for larger value of d in agreement with this condition. The other condition for good estimation is here on the plane with number of measurement and grid size. And the condition that we want here is that the distribution, the width, the uncertainty of the machine learning estimate must be much larger than the grid size. Okay, this is a condition to saturate, okay, the Kramer-Rao bound and the maximum likelihood estimation. And this condition corresponds to this inequality that quantifies the good estimation. In a sense, this corresponds to a well-resolved uncertainty. If this condition is not met, then we have strong fluctuation from one network to the other. So if we train differently the different network, we have strong fluctuations. And we don't have a saturation of the Kramer-Rao bound. So this is shown here in this figure, where I plot the variance of theta w, so I'm missing a w here, sorry, as a function of the number of measurements. So the blue line is our estimate, and you see that compared to the maximum likelihood estimate, the orange line. So you see that the machine learning estimate converges to the Kramer-Rao up to this dashed blue line, which corresponds to crossing this transition. And then we have a divergence between discrepancy, I would say, between the Kramer-Rao and the blue line, so our estimate, the uncertainty of our estimate. And you see in the shaded gray region, it shows the uncertainty if you repeat the estimation for different training. And you see that after this point, this spread increases substantially. I want to conclude telling you about a recent experiment done in Rome by the group of Marco Barbieri and Fabio Sciarrino in Rome. And they apply very recently in this PRL paper, a machine learning approach for phase estimation. So the experiment is very nice. It's one of the first doing this, applying this technique. However, the result seems in disagreement with our results. So here is their experimental finding, where I plot the sensitivity of the estimator as a function of theta. And you see that, so the experimental result are the symbols, while the solid line is the Kramer-Rao, and different colored line and symbols are obtained for different values of m. So essentially increasing m corresponds to this arrow, so going down with the sensitivity, with the uncertainty, and corresponds to this arrow here. So you see that the results disagree with the Kramer-Rao bound. However, this is in contradiction with what we found, but however, should be noticed that these results are obtained in a regime which is not the good estimation regime. These are obtained in the regime where the grid spacing is much larger than the sensitivity. So for comparison, I plot here as a dotted line the grid spacing 1/d. And so you see that experiment is done in this regime, where the saturation of the Kramer-Rao bound is not guaranteed according to what I told you. So I go to the conclusion. So in summary, I told you about the Bayesian and frequentist estimation of exploiting machine learning. The methods that I told you are completely general and are based only on bare data. So there is no model involved, no fitting in a sense, and these methods apply to any parameter estimation experiment. And indeed, I also discussed in the last slide a very recent experiment. The sensitivity that we obtain depends crucially on the grid size and number of training data, and I told you about optimal parameter for the neural network. What is interesting that the training strategies plays a key role and play the role of a subjective Bayesian prior, okay, in both methods, Bayesian and frequentist. However, this training strategy becomes irrelevant in the asymptotic regime where we repeat several measurements. And finally, I give you quantitative condition for the saturation of the Kramer-Rao bound for the frequentist and the Bayesian method. With this, I would like to mention again my collaborators, Samuel Nolan and Augusto Smerzi. I acknowledge our sponsors, and I would like to thank the organizers again for the invitation and for putting up this nice conference. And I thank you all for the attention. Thank you very much.
Thank you very much, Luca. Very interesting talk. So are there questions? I guess people are getting a bit sleepy at this time of the night.
Yeah.
So if I want to apply this in the lab, essentially the assumption is just that I need to be able to tune the parameter I want to estimate controllably in the training session.
Yeah, exactly. So you need your apparatus to be stable. So in order to acquire a good number of training data, so not an incredible large number of data, but a good amount of training data, and then you must be able to tune your grid parameter very finely. So you must have a good control of your parameter.
And once it's trained, then you can use it to measure the same quantity again, as you said, assuming that it's not changing over time. Yeah.
Yeah, exactly.
And I had another question noted down. And so this is also a very general approach, right? It can be used for any parameter estimation. It doesn't necessarily apply to quantum technology per se.
Yeah, no, exactly.
Yeah. So the only quantum thing would be that if you apply it to a large entangled state, then you would have no classical correlations somewhere in the.
Yeah, exactly. You are perfectly true. This apply also for any parameter estimation problem. And of course, our target is that of highly entangled and non-Gaussian and complex systems.
Durga has a question. Yeah, just go on.
Hi, Luca. Maybe I don't know if this question makes any sense, but if, for example, if I want to look at the reverse problem, like if I want to know, is there like for a given theta prediction of a given phase phi, is there an optimal measurement space subspace that corresponds to a given phi? So I want to go backward, like I want to find out what would be the optimal measurement result that could give me a best estimate of this a certain angle phi.
Okay, so if I understand correctly, you want to know what is the optimal measurement result.
Exactly, yeah.
Yeah, okay. In a sense, yeah, this is possible, and I think can be done with the Bayesian method.
Mm-hmm.
So you can find here the posterior Bayesian probability as for every measurement results. So you for different measurement results, you obtain essentially a set of these different distributions. And then the optimal one would be the one that has the narrowest width, where the probability is the most concentrated. However, the problem is that this optimal measurement result might appear very infrequently. So for the analysis, one has to also include the probability to get the specific measurement result indeed. But if you want to know what is the optimal measurement result, I would say this is the optimal, this is the answer.
Yeah, okay, yeah, okay, yeah, thanks, yeah.
Any questions from the audience? Yeah, somebody. So Lucas is asking, what kind of architectures for the neural network did you investigate in your studies?
Okay, this is a very technical question. Maybe the postdoc knows better than me, but I think it's nothing special. It's something that can be found open source. I don't remember exactly technically what is the neural network method. I cannot precisely answer this question. You have to give a look on the paper. So I'm sorry, but yes, for sure is something that can be easily implemented, relatively easily implemented. It's nothing, I would say, very sophisticated.
Any more questions? Doesn't look like. So I think we are about, you finished too early. We are about 10 minutes early for Chris. Let me check the program. Yes. And I don't see him show up. So I think we can just, everybody can take 5-minute break. And then we come back for a Chris Q&A. And yeah. And if you have any more questions for Luca, you still have time. Otherwise, post them on Slack and he will reply when he can. Thank Luca again. And
very much. Thank you very much. Bye.